Okay, so the characteristic polynomial of an n by n matrix is a degree n monic polynomial. The roots of that polynomial are the eigenvalues of the matrix, and the multiplicities of those roots as roots of the characteristic polynomial are the algebraic multiplicities of the eigenvalues. Now remember, when we studied polynomials previously, we discussed the Vita formulas, which were formulas that relate the roots to the coefficients of the polynomial. Let's see how that plays out with examples of characteristic polynomials. In particular, I want to look at the general formula of the characteristic polynomial of a 2 by 2 matrix, whose rows are A, B, and then C, D. Well, what we get when we take the appropriate determinant to calculate the characteristic polynomial is t squared, so we expected that because this is going to be a monic degree 2 polynomial, minus the quantity a plus d times t, plus the quantity ad minus bc. And if we stare hard at this, we realize that the coefficients of this quadratic are relevant to the matrix. The coefficient in front of t here is negative a plus d, while a plus d is the trace of our matrix. So the coefficient of t here is negative the trace. Then, when we look at the constant coefficient, ad minus bc, we realize that's the determinant of the matrix. So this gives us a cool formula for the characteristic polynomial of any 2 by 2 matrix. The characteristic polynomial of any 2 by 2 matrix is always t squared minus the trace of the matrix times t plus the determinant of the matrix. So what we're finding is that the characteristic polynomial has coefficients that are relevant to the original entries of the matrix. And if we think about what that so let's state this as a theorem first before we apply it. So it turns out that this is always true for an n by n matrix, and what I mean by that is this generalizes. So it turns out that the characteristic polynomial of every n by n matrix A always looks like this. We have t to the n, that's the monic part of the characteristic polynomial, so the leading coefficient is 1. Then the next term is always minus the trace of the matrix times t to the n minus 1. Then, generally, there's a bunch of other terms, and then we get to the constant coefficient of the polynomial, which is always negative 1 to the degree, so that's negative 1 to the size of the matrix, multiplied by the determinant of the matrix. So two of the coefficients inside of the characteristic polynomial, the coefficient of the t to the n minus first term and the constant coefficient, are related to the trace of the matrix and the determinant of the matrix. And those are exactly the two coefficients that our Vita formulas relate to the roots of the polynomial, which in our case now are the eigenvalues. So if we apply the Vita formulas to this formula for the characteristic polynomial, we get a trace formula and a determinant formula relating to the eigenvalues. The trace formula tells us that the trace of any matrix is always the sum of the eigenvalues, where each eigenvalue is multiplied by its algebraic multiplicity. We also get a determinant formula, and this determinant formula says that the determinant of any matrix is the product of all of the eigenvalues, where each eigenvalue is raised to the power of its algebraic multiplicity. So if you know all of the eigenvalues and you know their algebraic multiplicities, you can automatically figure out the trace of your matrix and the determinant of your matrix. So let's see an example. Here, somebody is giving us the characteristic polynomial of some matrix. So this matrix A has characteristic polynomial given by this formula here. And one thing to first observe is that this is a degree 7 polynomial, which means that the size of this matrix is a 7 by 7. The next thing to observe is that the coefficient in front of t to the 6, now 6 is 1 less than 7 here, is negative 2, And that tells us that negative 2 is negative the trace of our matrix. So the trace of whatever matrix we're studying here is equal to negative negative 2, which is 2. The last thing to look at here is the constant coefficient, plus 5. Well, what we know is that the constant coefficient is always negative 1 to the size of the matrix, so 7, multiplied by the constant coefficient. So the determinant of our matrix is negative 1 to the 7th times 5 here, which is equal to negative 5. So whatever this matrix is, it has to be 7 by 7 because its characteristic polynomial is degree 7. The trace has to be 2 because the coefficient of t to the 6 is negative 2. And the determinant needs to be negative 5 because the constant coefficient is 5. And the determinant needs to be negative 1 to the size of the matrix, which is 7, multiplied by the constant coefficient. So that's things we can infer about this unknown matrix just given the characteristic polynomial. Here we have another example. In this example, someone is giving us the factored characteristic polynomial. So the characteristic polynomial of this unknown matrix is t plus 4 squared multiplied by t minus 1 to the 7th multiplied by t minus 9 to the 3rd. Well, one thing we can immediately conclude are the eigenvalues, or we can figure out here are the eigenvalues. The eigenvalues are the roots here. So the eigenvalues should be negative 4, 1, and 9. So this matrix has 3 eigenvalues, negative 4, 1, and 9. We also know the algebraic multiplicities. For lambda equals negative 4, the algebraic multiplicity is 2. For lambda equals 1, the algebraic multiplicity is 7. And for lambda equals 9, the algebraic multiplicity is 3. Great. Now with this information, we can calculate the trace and the determinant. The trace is the sum of the eigenvalues, where each eigenvalue is multiplied by its algebraic multiplicity. So here we should get the negative 4 multiplied by its algebraic multiplicity 2, plus 1 multiplied by its algebraic multiplicity, which is 7, plus 9 multiplied by its algebraic multiplicity, which is 3. And when we add all those terms up, we get 26. So whatever our matrix is, we know that its trace is 26. We also have our determinant formula. The determinant formula says that the determinant of any matrix is the product of its eigenvalues, accounting for algebraic multiplicity. So here we should get the first eigenvalue, negative 4, raised to its algebraic multiplicity, which is 2. Then we multiply by the second eigenvalue, 1, raised to its algebraic multiplicity, which is 7. Then we multiply by 9, the next eigenvalue, raised to its algebraic multiplicity, which is 3. And when we multiply these numbers together, it turns out we get 11,664. So whatever matrix we're studying, we know that its determinant is 11,664. Cool. And we're able to conclude all this without even knowing the matrix here, because someone was kind enough to hand us the factored characteristic polynomial. Let's do one last example here. So in this example, we are given a 4 by 4 matrix, and we are told some of the eigenvalues, but not all of them. We're told that one of the eigenvalues is lambda 1 equals negative 7. We're told that another eigenvalue is lambda 2 equals 5. Another eigenvalue is lambda 3 equals 9. But we're not sure what the fourth eigenvalue is. So the question is, how could we quickly figure out this fourth eigenvalue? Well, this looks like a job for trace. We know that if we have all 4 eigenvalues, we know that we can't have more than 4 because this is a 4 by 4 matrix, and there can't be more than 4 eigenvalues because the degree of the characteristic polynomial would be 4, and a degree 4 polynomial can't have more than 4 roots. Great. We also know that if we add those eigenvalues together, that will give us the trace of the matrix. Well, we can quickly figure out the trace of this matrix by just adding all the diagonal entries. Negative 71 plus 35 plus 9 plus 30 equals 3. So the trace of this matrix is 3. Well, what about the sum of all the other all these numbers? Well, we'll get lambda 1 equals negative 7, plus lambda 2 is 5, plus lambda 3, which is 9. Well, what this is now telling us is that 3 should equal negative 7 plus 5 plus 9. What is that? Well, I guess that's equal to 7. So what this is telling us is that 3 should be equal to 7 plus the unknown fourth eigenvalue, which automatically forces our unknown fourth eigenvalue to be negative 4. So we've managed to figure out our unknown eigenvalue by using our trace knowledge. And we're able to do this really quickly because trace is really easy to calculate. So if you ever don't know only one of your eigenvalues, you can always figure it out with this method because the trace is always the sum of the eigenvalues.